Hello everyone, and welcome back to the Fluctus Channel. The B-52 Stratofortress remains the largest and oldest bomber still serving in the U.S. Air Force. A giant 8-engine bomber that first flew in the 1950s and is still expected to remain in service into the 2050s. Boeing built 744 B-52s, and the B-52H is the last operational version. A long-range heavy bomber able to carry roughly 70,000 pounds of weapons, fly at high subsonic speed, and operate at altitudes up to about 50,000 feet. That already makes it extraordinary. But one of the smartest parts of the bomber's design appears only when the mission is almost over. When the aircraft is lined up on final approach, still carrying enormous momentum, and has to surrender speed without punishing its brakes, wheels, and runway any more than necessary. The answer is a drag chute. A giant braking parachute that deploys after touchdown and helps tame the mass of a strategic bomber that has no business stopping quickly by normal means alone. Before that chute ever opens, the B-52 has already demonstrated why it remains such a useful aircraft. Weapons crews move beneath the wings and fuselage, loading bombs and missiles into a machine built to haul an immense variety of munitions. A B-52 can act as a nuclear deterrent, a conventional strike bomber, and a standoff missile truck, which is one reason it keeps surviving every attempt to declare it obsolete. Once armed, the aircraft taxis with the weight of a flying arsenal, lifts away behind 8 engines, and settles into the old bomber rhythm of climb, cruise, weapons, employment, and a long return. During training and combat support flights alike, the airplane still proves that size can be turned into strategic patience. The landing, however, is where the aircraft's age and cleverness meet most visibly. The B-52 is famous for its crosswind, or crab, landing ability. Because of its landing gear geometry, the aircraft can approach at an angle to the runway while the wheels still track properly on the center line. To anyone watching, the nose may appear pointed in the wrong direction even while the bomber is arriving exactly where it should. That trick matters because the Stratofortress has huge side area and long wings, which make crosswinds a serious concern. The bomber, therefore, does not simply descend and flare like a smaller aircraft. It manages wind, alignment, and momentum at the same time. Then comes the chute release. Once the wheels are firmly down and the timing is right, the braking parachute deploys from the rear of the aircraft. It inflates almost instantly, catches the air, and starts pulling against the bomber's speed. The effect is simple but powerful. Instead of leaving the brakes alone to absorb all the punishment, the aircraft uses aerodynamic drag to help slow down. That reduces heat, shortens the landing roll, and gives crews more confidence on long, wet runways or in difficult crosswinds. In a machine of this size, that extra control is not a luxury. It is part of how the bomber remains safe and practical after all these years. That brief moment depends on patient work that happens far from the runway. Chutes have to be unpacked, inspected, dried, folded, and packed correctly so they deploy cleanly rather than tangle or fail. Packing crews stage the canopy and lines with careful precision because a bad pack job can turn the smartest braking aid on the bomber into useless fabric. Maintenance teams then inspect the hardware, check condition, and prepare the system for the next sortie. So, the genius technique the B-52 uses to slow down is not just the deployment itself. It is the whole chain of design, packing, inspection, crosswind handling, and timing that lets one of the largest bombers ever built finish its flight with a giant controlled handbrake made of air and cloth. The B-52 is not alone in relying on a parachute to finish the landing. The same idea appears whenever aircraft speed, runway conditions, or sheer mass create more stopping force than brakes alone can comfortably manage. The F-4 Phantom is one classic example. Built for speed and power, it often used a drag chute after touchdown to help control rollout and preserve brakes on long military runways. On a fighter, the chute opens with a much sharper violence than on a bomber, but the principle is identical. Let the air help stop what the engine's already accelerated. A more modern version appears on Norway's F-35A drag chute variant. Because of icy runways, harsh winter weather, and strong winds, the aircraft uses a dedicated drag chute housing mounted between the vertical tails. That detail says something important about aviation. Even on a stealth fighter loaded with software, sensors, and advanced flight control systems, an old mechanical idea can still be the best answer once the wheels are down and the runway is slick. In that case, the parachute is not a relic. It is insurance shaped by geography and weather. The same logic even reached space. The space shuttle eventually adopted a drag chute to help slow the orbiter after landing. Once the shuttle touched down and stopped being a spacecraft for those last moments, it still had to solve the same problem as every other high-speed glider. Too much speed, too much mass, and not enough reason to trust wheel brakes alone. The chute reduced rollout distance and brake wear, proving that the simplest aerodynamic brake could serve a bomber, a fighter, and a returning spacecraft with equal intelligence. Seen together, these aircraft prove that the drag chute is one of aviation's most stubbornly useful tools. The B-52 uses it because it is huge. The Phantom used it because it was fast. Norway's F-35A uses it because weather can punish even the best landing. The shuttle used it because physics never offers exceptions. Different aircraft, different missions. Same clever answer. Use drag before heat, and mechanical stress take over completely. Parachutes are not only for slowing aircraft after landing. In modern logistics, they have become steering devices that can guide cargo with surprising precision. That is the idea behind the Joint Precision Airdrop System, or JPADS. Instead of dropping supplies under a simple canopy and accepting wide drift, JPADS combines a steerable parafoil, GPS guidance, and an onboard control unit to guide cargo toward a planned impact point. The parachute is still slowing the load, but it is now doing something more sophisticated than just falling safely. The process begins inside the aircraft. Pallets or containers are prepared, matched to the guidance kit, and loaded in a release sequence that supports a clean exit. Once the cargo leaves the ramp, the parafoil deploys. the control system starts working, and the load stops behaving like dead weight. Winds, release altitude, and route still matter, but the parachute is now steering. That means aircraft do not always have to fly directly over the exact delivery point. The parafoil can absorb part of that burden after release, allowing the drop aircraft to stay offset and reducing exposure, while still bringing supplies closer to the troops who need them. J-PAD's loading also demands careful rigging. Crews secure the bundle, fit the parafoil, verify the guidance unit, and calculate release data before the aircraft reaches the drop point. Once released, the system is not simply drifting. It is working through commands, adjusting the canopy, and trying to arrive where planners need it, rather than where the wind alone would send it. That transforms airdrop logic. A parachute becomes a quiet form of guidance, turning what used to be approximate logistics into something much more deliberate. In that sense, the same air resistance that slows a bomber after landing can also become a tool for battlefield precision when attached to cargo instead of a tail. Parachutes also appear in weapons delivery, where the purpose is not safe landing, but controlled extraction, stabilization, and timing. During early MOAB test work, parachutes help pull the massive weapon clear of the aircraft and stabilize its initial release sequence. In the Rapid Dragon palletized munitions concept, missiles are loaded on pallets, extracted from cargo aircraft through the rear ramp, and deployed under parachute before separating and continuing toward their targets. Even smaller munitions sometimes use tiny retardation devices to control attitude, timing, or spacing after release. That same principle explains why retardation parachutes on bombs or extraction chutes on palletized missiles matter so much. They buy order, orientation, and control in the first critical seconds after release. In aerospace, drag is not the enemy. Used correctly, it becomes part of the design. That means the same broad idea keeps reappearing throughout aerospace. A parachute can slow a bomber after touchdown, guide a supply pallet toward a drop zone, stabilize a huge bomb, or help turn a transport aircraft into a temporary missile carrier. Different missions, different scales, same brilliant principle. Use drag intelligently. That is why the B-52's landing chute belongs in a bigger story than runway braking alone. It is one expression of a much older aerospace habit, using fabric, lines, and air resistance to solve problems that brute mechanical force handles badly. In the end, the B-52's genius landing technique says something larger about military aviation. The biggest and oldest bomber in American service does not rely on a futuristic miracle to slow down. It relies on a practical, brutally effective solution prepared by skilled hands and timed by experienced crews. The same family of parachute logic then stretches outward to fighters, spacecraft, cargo drops, and munitions release. Different aircraft may dominate the headlines for speed, stealth, or firepower. But the quiet technologies that help them land, deliver, and survive are often just as important. The B-52 proves that every time the giant chute opens behind the tail, and one of America's oldest bombers finally gives up its speed to the air. That is the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.